Welcome back to COSC 2325. This is Chapter 2, Part 2. In this video, we're going to talk about memory management, the 64-bit processors, as far as the components of the 32 microcomputer architecture. I'm going to have just a YouTube video out there for you to watch. You can just read the chapter on this part. It's just about the internal parts of the computer. And then I will discuss the input-output system. Okay, we're going to talk about how the CPU manages memory through these different types of CPU modes. So CPU modes, you may have heard it being called processor modes or CPU states or CPU privilege levels. So these modes are just operating modes for the CPU, how the CPU is operating. And what it does is it places a restriction on the type and the scope of operations that can be performed by processes that are run by the CPU. So if there's a CPU is running a process, it can decide what restrictions to put on that process. So the different types of the 86 processor modes of operation are protected mode. Within protected mode, there's a sub-mode called virtual 8086 mode. There's the real address mode and the system management mode. So let's look at each of these. So protected mode is the most robust and powerful, and the mode that basically just protects programs from writing on top of other programs that are running at the same time. So when you open a program, that program is assigned a memory partition if it's running on protected mode. And that program that's in that partition cannot write to another program that's running on a different partition. So this is designed for multitasking. And the only drawback with protected mode is that it will restrict application programs from directly accessing system hardware. So it's nice because it will protect programs from writing in memory locations that other programs are running, so their partition is theirs and cannot be overwritten. So it's designed for multitasking. And again, multitasking just means that you can have several applications opened at once. So you can have your browser opened while you have while you're playing a game, and then another window may have Microsoft Word running and PowerPoint. So you have all these different applications that are running. And multitasking was not available until like when Windows ran just MS in MS-DOS, then we could not do multitasking. So we could only run one program at a time. Once it came out with what we call this nice graphical user interface, then multitasking was available. So protected mode is supported by Linux and MS Windows. And then we have real address mode, And real address mode means that you cannot multitask. So the processor can run only one program at a time. The processor can interrupt that program, stop it, and then make a request to a peripheral like the printer, or it can stop that process and just do something else. Applications in real address mode are permitted to access any memory location, even those linked to system hardware. So if you remember, in the protected mode, it's not allowed to access system hardware directly. MS-DOS, MS-DOS was real address mode, was not multitasking. Windows 95 and 98 did run in protected mode, but it started in real address mode. So it would boot up in real address mode, and then it would switch to protected mode. So Windows 95 and 98 are multitasking, or were multitasking operating systems. But they were, you could not open a ton of applications because it would slow down your system, but that had to do more with the memory, how much memory it had. I can't remember if I talked about this or not, but whenever you open an application, the instructions that are needed to run that application are in RAM. And so if you have 10 applications that are open, then you're going to need X amount of RAM to run each one of those. Also, with protected mode, it actually reserves a certain amount of space for each application. So you can open a lot of applications, but depending on how much memory you have, you could run out of memory, and then it slows. It won't let you open that application if you run out of memory. Then the virtual 8086 mode is a submode of the protected mode. And what this does is, while you're in protected mode, the processor can safely execute real address mode software. So what it does is the virtual 8086 mode creates an environment that's named virtual 8086 mode, and this environment is it's protected away from everything else that it's running. So we call it like a sandbox-like environment. This term sandbox is used whenever you have something that you are not implementing and you're just playing with it, like children playing in a sandbox. So you're testing something or playing with it. That's how that term sandbox is used. System management mode. In system management mode provides its host operating system with a mechanism for implementing functions such as power management and system security. So it provides the operating system with a way to or a mechanism for implementing functions. These functions are usually implemented by the computer manufacturers who customize the processor for a particular setup. So the system functions are usually implemented by the computer manufacturer. And they're typically in BIOS, which we'll talk about here later, which are your basic input-output system functions. So in this course, like I said before, we're going to program in assembly language using the MASM assembly language. There are different types of assembly languages, like there's MASM and TASM, and they both have different instructions. So different instruction sets, different keywords that you use to program. But both of those you can program for the 32-bit processor, right? With MASM, you can also program for 64-bit or 32-bit. But when we program for the 64-bit, we have to learn, there's like different names for the registers, and sometimes there's different ways for doing different things. So for this particular class, we're going to stick with the 32-bit processor so that you don't get confused, because just learning the 32-bit processor instructions that we'll be using is going to be enough. But we are going to look just to see what are some differences between programming the 32-bit and 64-bit processors. So the 64-bit processor is backwards compatible with the 86 instruction set. It addresses are 64 bits long. So 32-bit processor, the addresses are 32-bit long. It allows for a virtual address space size of 2 to the power of 64, which is about 17 gigabytes. Or it's more than 17 gigabytes. In current chip implementations, only the lowest 48 bits. So if you think of this is the size that you have available, it uses the lowest bits would be from this direction this way. So it uses the lowest 48 bits. It can use 64-bit general purpose registers. So remember 32-bit, the registers are 32-bit, the size of 32 bits. And because you have 64 bits, it allows for instructions that have 64-bit integer operands. So we're going to see when we program in 32 bits, for a 32-bit processor, that we can make large calculations, but we have to use two 32-bit registers to be able to do that, and a special instruction. 32-bit processors, they use 8 more general purpose registers than the 86. So we have 8 general purpose registers for the 32-bit processor. We have 16 for the 64-bit processor. And it uses a 48-bit physical address space. And that's because, remember, we only use the lowest 48 bits, which supports up to 256 terabytes of RAM. Okay, and I said this earlier, the 64-bit processor has 16 64-bit general purpose registers. It has 8 80-bit floating point registers, which is just like the 32-bit. The status flags, remember in the 32-bit processor, the status flags register is called E flags, and it is 32 bits. For a 60-bit processor, it is a 64-bit status flag register, but it only uses the 32 bits, the lower 32 bits, because you just don't have that many flags, so you don't need to use it all. And in a 64-bit instruction pointer, it's called RIP, and in the 32-bit processor, the the instruction pointer is called EIP. So again, make sure you read the section in your book that talks about the components of the microcomputer. And I'm going to go on to the input-output system, which will be the last thing that we cover. So you're going to look at the motherboard and all the parts, and this is a really fun section to actually read, so take some time and read about it. There's some really good videos that people have out there that will talk about the motherboard and all the different parts, you know, of the motherboard. And again, if you've never built your own computer, it's actually interesting even if you don't like hardware. I had the experience of building my own computer early on in my career, just because it was, at that point, it was cheaper to build it myself. So it's a good learning experience. So it talks about video output, different types of memory, which you've probably covered before, but go ahead and read about all the different types of memories. And what we're going to be, when we program, we're just going to be using, of course, ROM. That's what we're going to be concerned with. It's about the different ports, device interfaces. Okay, so the input-output system. So when we talk about the input-output system, we're talking about, for example, when you're writing a program, you can get input. You typically get input from the keyboard or the mouse. If it's a graphical user interface, you'll get input by the user clicking on a button. And then you output typically to the screen, or you output to a file, or maybe to the printer. Okay, so that's what we call about input output. So there's different levels of input output. And what we mean is, like, if in level 3, so level 3, we have the high level languages. So the high level languages, what they do is they use a function to actually write to a file. Okay, so if they want to write to a file, we'll use a function. Or if you want to print to a peripheral, like print to the printer, we're going to use a function for that. So because the high-level languages use functions to get to things that are that the operating system actually typically accesses, then we call the input-output to be a portable. It has a high portability, because you can take this program that you create in this high-level language, like let's say Java, and run it on any system. And because of that a function that it uses, it can access things that the operating system will take care of, but it does it through the highest level function. So the function basically accesses the operating system's API, and then the operating system API goes to the BIOS, and the BIOS is the one that accesses, let's say, the hardware. So it does take the trip like this, you know, it has to go 1, 2, 3. So because it has to do that, it's not always the fastest, but it's convenient and it's portable. Now what we call level 2, programmers can call operating system functions from this application programming interface, the API library. And through that API library, then they can access, let's say, system functions or hardware. And then we have level 1, which is your basic input-output system. BIOS stands for basic input-output system. And the basic input-output system is just a collection of very low-level subroutines. Subroutines are like functions, and those subroutines or functions, they communicate directly with the hardware devices. The BIOS is installed by the computer's manufacturer, so it's read-only memory, and it's tailored to fit the computer hardware. And the operating system is the one that communicates with the BIOS. So operating system communicates with the BIOS. All right, so let's say that we wanted to display a string of characters with a high-level language. Okay, so these would be the steps that we would have to take to display a string of characters with, starting here with our high-level language. Let's say we created a program in Java, okay? So there's a statement in the application program which calls the high-level language library function that writes the string to the standard output, meaning the console, the screen. The library function, which is level 3, calls an operating system function, passing it a string pointer. So you, as a programmer, use this function, and it's like magic. It goes and it writes stuff for you on the display, but what you don't know is that that library function that, let's say, Java has for you to use has to actually pass this string pointer to an operating system function right here. But you don't have to do that. You just have to call this little function and give it the string that you want to write to the console. So then the operating system function, so we're at level 2, uses a loop to call a BIOS subroutine, passing it the ASCII code and the color of each character. So you've got a string. Let's put a string here. Hello. H-E-L-L-O. And all you had to do was give it to a function, and boom, it shows it on the screen, right? Well, to level 2, you had to pass it a pointer, or the Java language had that function that you use actually has to pass a pointer to the string. The pointer basically just points to the first letter of your string, and that's passed to level 2 with the color. No, sorry. In step 2 is just we're passing it the string pointer to here, and then from here, here at this point, it has to go through and loop through this entire string. So 1, 2, 3, 4, 5. There's 5 characters, so it's going to loop 5 times, and it's going to pass the ASCII value of H to BIOS with the color of what H is. Then it's going to pass the ASCII value of E and color, etc., etc. Let's see, then the operating system calls another BIOS subroutine to advance the cursor to the next position on the screen. And then the bio subroutine level 1 receives a character. So from here, it's going to receive the character H. As ASCII, it's going to map it to a particular system font and sends the character to a hardware port attached to the video controller card. The video controller card, level 0, generates timed hardware signals to the video display that controls. So let me see here. So we did not, this is not here. It goes, the H gets passed from the operating system to BIOS, and then here is where we access the hardware, which is the video controller. Okay, so that was a lot of steps, and what you don't need to know the steps, you don't need to memorize what are the steps and what happens. All that you need to know is that with assembly language programming, assembly language can actually have access to all those levels. So with assembly language, you can access the hardware, the BIOS functions, the operating system functions, and the libraries. So you can perform input-output at all the different levels. Whereas with high-level languages, we cannot do that. So with a high-level language, we're up here, and it's like magic. We say, cout hello, and it couts hello to the hardware, but it has to go through all these levels. Okay, so this is the end of chapter 2. I suggest that you look at the end of section review questions and the end of chapter review questions before you take your quiz for chapter 2. Okay? Thank you. And here's a fun exercise. You can go find the ASCII table. You can just search that up online and figure out what this says. Okay guys, see you in the next video. Thank you.